Hi everyone. Our task is about environmental sound classification. This technique can be applied for audio scenes recognition, city noise reduction system, etc. First, let me introduce our dataset. Our data is from the Urban Sound 8K dataset, which contains 8,732 labeled sound files. All of them are shorter than 4 seconds, and they are separated into 10 different classes. The raw data has two parts. The first part is about metadata, which keeps the basic information of each audio file. From here, we can extract the target and the parsing parameters. The second part is the time domain audio data distributed in 10 folds with 800 to 1000 in each fold. Then we came to the pre-processing step. We applied audio data augmentation, including time stretching and pitch shifting. Here is a demonstration of the time stretching. The original audio. The time-stretched audio. And the pitch shifting. In consideration of keeping the audio meaning unchanged, the candidate factors we chose are in a reasonable range. By applying data augmentation, the classification accuracy increased by nearly 2%. Next, we transformed the raw audio data into Mel-scale spectrogram. It represents the spectrum of frequencies as it varies with time. 4 examples are shown here. The dog bark data has multiple strong pulses in short time. The gunshot data contains 1 or 2 sudden pulses and a long lateral remaining for a while. Air conditioner power spreads widely across time and frequencies. Drilling data has stronger power within the middle frequency area than the higher and lower part. Finally, to avoid generating pre-processed data repeatedly, about 1 hour each run, pre-processed data is stored in HDF file format with 10:1 compression ratio. It only takes around 10 seconds to load pre-processed data before we train our model.
I'm going to talk about training model that we finally choose and the training method. For the training model, the architecture is like this. We use 3 convolutional layers, so the model is called CN3. The input is n times 128 times 128 mile-scaled spectrogram, and the number of the channel is 1. For the 2D convolution layers, we use 24 filters for the first 2D convolution layer and 48 filters for the rest layers. The size of each filter is 5 times 5. The stride is 1 for each dimension, and the rectified linear unit activation function was used for each convolution layer. For each max polling layer, the pole size is 42 and the stride is the same as pole size. The dropout rate is 0.5. For the first fully connect layer, we have 64 units and the activation function is rectified linear unit. And for second fully connected layer, we have 10 units, and activation function is softmax. When the model is compiled, we choose Adam as optimizer because it is fast for training, and it can correct bias. The number of epoch is 50. The batch size is 128. The loss function is category cross entropy cos loss function. The performance metric is accuracy, and we have over 200,000 parameters in total. In the original audio folders, each audio may have relationship with others in the same folder. But for different folders, audios are independent. So we choose 10-fold cross-validation. Of the 10 folders, a single folder is retained as the validation date for testing the model, and the remaining 9 folders are used as training data. The cross-validation process is then repeated 10 times, with each of the 10 folders used exactly once as the validation data.
Now let's introduce the process of training the CNN model. In the notebook, we will take the model named CNN3 for example, which performs best compared with other models we use. At the beginning of the training process, we need to import the libraries which will be used, including Keras, NumPy, and H5py. First, let's look at the first part of the code. This part of code is used to load training data from H5 file. As the dataset is already divided into 10 folds, we perform 10-fold cross-validation in this part. For simplicity, we only focus on one of the 10 folds here. The training date contains the date, augmentation date, and their labels. And we printed the shape of each fold of the training data here. We can see the numbers of data in each fold are almost equivalent, and the input shape of all data is equal to 128 multiplied 128. Then we split the training set and test set here. In each round of the cross-validation, we use data from one fold as the validation set and the data from other 9 folds as training set. Then we use sequential model in Keras to define the CNN model. In the example, we define 7 weight layers including 3 convolution layers, 2 max polling layers, and 2 full connect layers. Besides, we also use 2 dropout layers to avoid overfitting, and the train hyperparameters have been introduced before. Next is the main body of train. In the train process, we got the best performance at epoch 50, and in order to print the result concisely, we only train the model for 12 epochs in the notebook. In the example round of 10 folds across validation, we train the model on 15,825 samples and validate on 837 samples. Each epoch took nearly 8 seconds, and the final test loss and the test accuracy after 15 epochs are 1.44939 and 67.28% respectively. At the end of the training process, we save the training process as a log file in order to draw some curve pictures and to analyze the model. For CNN3 models, we draw the loss curve and accuracy curve for each fold. Obviously, data from some folds have much lower classification accuracy and higher test loss than others just like fold 2, in which there is an uneven distribution of data types.
In order to evaluate the capability of convolutional neural network to extract features from environment sound, we also set up control experiments. In addition to CNN models, we set up control groups using MFCC features plus evidence classifiers. MFCC feature is a popular feature that widely used by many previous researchers, and FMN model is really simple for us to implement in this situation. According to this result, we can easily find that CNN models outperform the other groups. So we can draw a conclusion that though CNN models haven't achieved excellent performances as being used in computer vision area, it is still the more effective extractor for environment sound classification problem. Then we move forward to the analysis within CNN models. The accuracy of CNN3 after training 50 epochs are shown in this table. We can easily find that the class that with highest accuracy is gunshot, while the worst one is air conditioner. Refer to one of the confusion metrics. We can find that the audios of air conditioner are always being mispredicted as engine idling and jackhammer. Furthermore, when we refer to the male spectrogram patterns, the well-predicted classes like dog, bark, and gunshot might have their unique patterns, while the classes with worse performance like jackhammered and air conditioner is really confusing and hard to make decision even by a human. It means that CNN is good at detecting the unique 2D texture patterns if we regard the mouse spectrogram as a 2D image. Last, let me present 3 examples. As I use the models saved from Fold 1, the test audios are also picked out from Fold 1. Then the first audio is a dog bark audio. It is predicted correctly. Then it's a gunshot audio. It is predicted correctly. The last one is the jackhammer audio. It is also correct. Here's the end of our video. Thanks for listening.